Hello, we're going to deal with a philosophical lecture today, the notion of space and time. So let's jump into it and see where we go. Just give me a second. We'll get cranked up here. Here we go. Okay, so this was stimulated by a book that's come out by Karen Crowther. She's actually a philosopher. And so she's grappling as a philosopher with topics that arise in pure mathematics and in theoretical physics. And collectively, she's called them effective space-time, understanding the emergence in effective field theory and quantum gravity. So let's see where this takes us. We're going to give you an outline here. We're going to deal with what we think the problem is, what Newton had to say about that, what Einstein said. Then we'll go into the microscopic realm of quantum mechanics and quantum field theory. We'll touch on thermodynamics and then describe effective field theory as a patchwork to try and deal with a lot of these things. The notion of emergence of theories, and then go into quantum gravity and decoherence, time classical to quantum. So here we go. The problem we're dealing with here, general relativity, is a classical theory that works on the macroscopic scale and has no microscopic quantum version that's been accepted to date. However, quantum mechanics works on the microscopic scale, but hasn't had a macroscopic classical version to date. So it's only when these two are in the same realm. So when in the world is the macroscopic and the microscopic comparable to one another? Well, when gravitational forces are significant on very small microscopic scales, then that's when general relativity and quantum mechanics meld into one another. So this would occur at the start of the Big Bounce when our universe was created. And so everything was within, there's various numbers that are thrown around. You know, the entire universe was a couple meters across, for example, even though today it's, billions of light years apart. You can see that things got crunched. And so what was microscopic becomes macroscopic in that realm. Now, how in the world do we come up with a single all-encompassing, self-consistent theory of gravity that works on both the microscopic and the macroscopic scale? That's the conundrum we have here. This is what has been pushing physics. And a lot of the indications are, by the way, that this could be the wrong problem, but that what we should really be looking at is the underlying geometry of space and time, and that's what we'll argue at the very end. So what did Newton have to say about this? Newton created three laws of physical laws that describe motion of an object and the forces acting on it. And so these three laws are paraphrased as follows. A body remains at rest or in motion at constant speed in a straight line, except insofar as it's acted upon by a force. This sounds pretty innocuous. At any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalently, the rate at which the body's momentum is changing with time. Momentum is the velocity multiplied by the mass, is a rough approximation. So if there are two bodies that exert forces on each other, these forces will have the same magnitude, but equal in opposite directions. And this occurs in the arena of space-time, where space encompasses three dimensions. Time is a separate dimension, behaves like a dimension. It's totally independent of space. Gravity is an example of a force. Remember, Newton's laws applied for any force. So gravity is a particular force between two objects that's proportional to the product of the mass of each object and inversely proportional to the square of the distance between the two objects. the square of the inversely proportional square of the distance comes about from geometry. If we look at say a mass of some sort, say the sun, and we put a sphere around it of radius r, then all of the gravitational energy will get smeared out across the surface of that sphere, and the area that's on that sphere is from simple calculus 4 pi r squared. So if we double the radius, say we go out twice as far, then now the radius is 2r, then the energy is still all there, but it's smeared across a radius, across a sphere that is 4 pi times 2r squared, or 4 times r squared. Or in other words, it's a fact, if we double the radius, the gravity is smeared out over something that's 4 times the area, which leads to the statement that the gravity is inversely proportional to the square of the distance. That's how we come up with that. Give it some thought. So Einstein went into general relativity and space-time, and he observed that general relativity, or his general theory of relativity, is a geometric theory of gravitation. He came up with this in 1915 after a decade of work. He refined Newton's laws of general gravitation and provided a unified description of gravity as a geometric property of space and time, but this was now a 4-dimensional space-time. Time and space were coupled to one another. So in particular, the curvature of space-time is directly related to the energy and momentum of whatever matter and radiation are present, and the relation is specified by the Einstein field equations, which are a system of second-order partial differential equations. Now, Newton's law of gravity as a prediction of general relativity for all kinds of run-of-the-mill ordinary cases where gravity is not, shall we say, incredibly strong. This means equivalently that the space-time we're dealing with really doesn't have any curvature. That means almost flat. And so some of the predictions that we come up with here come out of classical physics and are fine. But when we look at things like how light propagates as it goes from one star past a star to us, we observe it, the light will actually get bent, the path of the light, by the strong gravitational field of that intermediate star. If we increase the gravitational field, time slows down. So gravity and time are clearly coupled to one another. We have so-called gravitational redshifting of light, which means that when you look at the spectrum of a distant star or galaxy in particular, you'll see that the entire spectrum is typically shifted to the red side of the spectrum. We have ultraviolet going on up to red, and that means that it's moving away from us, and that is due to this so-called dark energy that is expanding our universe. And this also leads to the issue of what are called black holes. These are singularities that are so strong in gravity that even light can't escape from them. The center of the Milky Way galaxy is estimated to have a black hole at the center of it that's 4 trillion masses of the sun. So it's, if you could imagine 4 trillion suns stuffed into a very, very small area, that's a black hole. Every galaxy that we've seen appears to have these black holes in the center of them. There's one that actually has 100 trillion suns for its black hole as a mass, for example. These numbers are inconceivable. So far, all of the tests of general relativity have been shown to be in agreement with theory and so forth, but this also led to the discovery of the so-called Big Bang, which we now realize is the Big Bounce. That because everything is moving away from us means that everything started at the same point. And if everything started at the same point, that's where the bounce occurs. That was the start of our universe. Now we go off into quantum mechanics, which is a fundamental theory developed about 100 years ago for the behavior of nature at and below the scale of atoms. So it's really the foundation of what is called quantum physics. And this includes quantum chemistry, quantum field theory, any sort of quantum technology such as lasers or light-emitting diodes, and quantum computing, quantum information science. So quantum mechanics can describe many systems that classical physics can't. The classical physics can describe many aspects of nature at an ordinary or macroscopic and optical macroscopic level, but it's not sufficient for describing them at very small levels, and things break down. This started, for example, with looking at the radiation curve for a so-called black body, and the classical theory suggested that the radiation would become infinite when in fact it would drop to zero as you looked at lower and lower wavelengths, which stimulated all of this work. Most theory in classical physics is derived from quantum mechanics as an approximation to these scales. Now, quantum field theory is actually what underlies quantum physics, quantum mechanics here. And the realization here is that things that we think of as particles are not in fact particles, they're actually fields. So for example, an electron is an entity that many people think of as a particle. It behaves like a particle in many ways, but in fact, it has wave-like properties. So in particular, an electron has 10 vibrating strings that are closed, that circle around one another, and they're vibrating at such a rate that they capture energy inside them. And so the energy is created in a torus, in a donut, but it's the hole in the middle of it is very small. So the electron by itself appears to be a particle, but in fact, it's this resonant energy that's inside these 10 vibrating strings. And that, in fact, is the crux of quantum field theory. Other particles, such as the basic fundamental particle that we deal with here, is the subquark that, again, consists of 10 closed vibrating strings. And that the subquarks make up quarks, and the quarks make up protons and neutrons that we find in the nuclei of atoms. This is a very key thing to keep in mind here. When we deal with dark matter, the only difference here is that dark matter is matter that has only 5 strings, and the 5 strings vibrate very rapidly and capture energy. And so all of this energy is captured inside the 5 strings, but there's no charge associated with the dark matter. So the dark matter by itself just exists on not on the scale of matter that we're used to, with electrons circulating around a nuclei that consists of protons and neutrons, but instead the nuclei scale that we're dealing with here for dark matter is entirely made up of these subquarks, and they're bound together one another by gravity, by the attraction they have vibrating for one another. So the current model for physics is all based on this quantum field theory, and it's called the Standard Model. It was arrived at 50 years ago, and there's been relatively little tweaks to it ever since then. The quantum field theory treats particles as excited states called quantum levels that are underlying the quantum fields, and these are more fundamental than the particles themselves. And there's equations of motion that are computed by using a Lagrangian rather than what Newton had. Lagrange came along and looked at what Newton had and came up with a alternate postulation of Newtonian mechanics based on Lagrangian action functional, and so it goes. So having said that, all of these interactions we described by a Feynman diagram that Richard Feynman received the Nobel Prize for. And if you can keep track of all these things, you know what's going on. Thermodynamics is a branch of physics that deals with heat, work, and temperature. And so it's an aggregate theory. We can't possibly compute all the interactions of the 10 to the 23rd molecules in a liter of air, for example. But we can compute gross properties such as the pressure and the temperature and the heat capacity and so forth. And so this evolved out of this as a theory of laws, the first law being conservation of energy. The second law came to be the conservation of entropy, and the third law came to be the notion of absolute zero, that there is in fact an absolute zero temperature that nothing can get lower than, and that led to real revolution in what is called superconductivity. The initial application of thermodynamics was really toward making better steam engines, and this was active from the middle of the 1700s on up to today. Then there's all kinds of chemical thermodynamics that go into this, that explain how chemical reactions occur and so forth. Then we come up to effective field theory, which is a type of an approximation. This is where nothing seems to work, so we're going to glue something together as an underlying physical theory based on some sort of model, some sort of conception of what's going on, such as quantum field theory or some sort of statistical mechanical model. So we have to get enough stuff in here to get the job done. We average over the behavior at the appropriate scales that we're interested in. And this thing really seems to work well when there's a large separation between different scales. For example, going from atomic scales going on up to very large molecular scales, very different things arise here. So this is another thing in the bag of tricks of physicists. Emergence is something that's come about through physics when they were trying to describe superconductivity as an example, but it's also come about in a variety of other ways. You have something where there's something that's very complex in its behavior, and nothing seems to work on their own, and yet there's an order that occurs when they act as a wider whole. So this emergence plays a central role in theories of integrated levels of complex systems. For example, life. How in the world do you explain life? Or consciousness, which is observed from a bunch of chemicals, which are made up of a bunch of atoms. What in the world is going on here to create consciousness, or consciousness is an emergent entity? The thing that I'd like to point to is the central limit theorem of probability theory. So if I flip a fair coin n times, and I record a +1 when I get a head and a -1 for a tail, and then I keep adding up the sum of +1s and -1s for each flip of head and tail, and divide this by n, then it'll converge here when I look at this thing to some sort of bell-shaped distribution. So I have this order that occurs out of nothing. There simply are heads and tails, +1 and -1, and so it goes. Quantum gravity is a field of theoretical physics that tries to describe gravity according to the principles of quantum mechanics. The problem with this is there is no such theory as we see it here today, but it's something that's of very active interest, and we'll see where it goes. Decoherence is a quantum issue. When you have quantum coherence, you end up with things being in a set of locked-in states. They're all synchronized to one another. But when they lose their synchronization, for example, all of the electrons are all spinning upwards. Okay, they're toward. If you think of the electrons as being on a tabletop, all of them are spinning up. Are all going clockwise, for example. So their spins are all up. But decoherence occurs when this breaks down, when some of them start to spin down and up, and they start to flip back and forth between these things. This leads to this notion of decoherence. So quantum computing relies on quantum coherence as an example of how to create a quantum bit. Just to expand on this decoherence thing, since it's one of these things that comes up again and again. If a quantum system were perfectly isolated, then it would stay in the state, whatever it is. The only problem is that we want to go investigate it, and if we choose to investigate it, then we poke at it, so it's no longer perfectly isolated, and then it has the chance to become decoherent. And so it goes. So this is really a loss of information that occurs in this thing, and the dynamics of this are irreversible. Once you start to get decoherence, you can't go back there. So you have to think, how in the world do I actually get in this coherent state? So let's look some more at what's going on here with space-time, since this is where we think the action is. And what we're saying here is that it's probably more fundamental to look at the arena, at the underlying geometry, and not so much to look at the parts, for example, the forces and the fields and so forth. So the universe is in fact made up of a 26 real dimensional universe, and it has a lot of structure to it. There's 10 dimensions for matter, 10 dimensions for dark matter, and there's 6 dimensions here that synchronize between the two 20-dimensional subspaces. We have 4 dimensions here for space and time for matter, and an orthogonal subspace here for 4 dimensions for space and time over here. And then we have 18 compactified dimensions that are each in 6 real dimensional subspaces. If we did everything in complex dimensions, we'd have 24 spatial dimensions and 2 dimensions for time, 1 for matter and 1 for dark matter. So the 24 spatial dimensions would be actually 12 complex dimensions, thinking of complex numbers. And out of those, we have 18 real dimensions, or 9 complex dimensions. And the space-time for matter is where we live, where the space-time for dark matter is where things like souls and spirits live. There are, with these 18 dimensions that are all compactified here, we have 3 holes in the matter, 6 compactified dimensions. They're going to connect to the 3 of the 8 holes in the synchronizing space. There's going to be 4 holes in the compactified dark matter that connect to 4 holes here, and the final hole connect to 2 of the 6 dimensions here. So we actually have only 10 dimensions here in this whole 18-dimensional space. But this is exactly what the mystics saw in the Kabbalists, the tree of life having 10 nodes, or sephiroths, that occurred here. So let's look some more at this to see what else is going on. A key thing here is why the geometry is fundamental, is that that space is in fact a foam. It's made up of compartments, and they're coated with information, and the information blocks are constantly scanning, and when they detect a change, they check with their algorithms and act upon whatever the change is, the algorithms say, okay, now do this, whatever that is. So the information, in fact, controls everything that's happening here. And this explains, for example, the double slit experiment in physics, where we shoot electrons at a single slit. They go through the single slit in a straight line. You see a line of electrons on the other side. When we put in two slits close to one another, we shoot electrons at it, we get a wave pattern, we get a series of interferences of highs and lows on the other side. So the electron is now behaving like a wave, but that's because the electrons are scanning, they're coated with the information blocks, and they see that there's in fact one or two slits. There's one slit, they behave like a particle. There's two slits that behave like a wave in going through, and this is what underlies everything. David Bohm arrived at a theory of quantum mechanics, which includes this type of behavior. He called it a pilot wave for explaining what's going on. Another thing that occurs here that's hidden, as we mentioned, that there's 26 real dimensions. It turns out that mathematicians spent 150 years looking at symmetries. This is symmetries are where I rotate something or I flip something around its diagonal and on. And these make up symmetries that are called finite simple groups. And after 150 years, they came up with 20 categories that are shown here for these finite simple groups. What's amazing is that the study of symmetry resulted in things that were, in some sense, not really symmetric. There are 26 sporadic groups, which are shown down here, 26, which magically matches with the 26 dimensions that we have. So in fact, each of the 26 dimensions that we have, there are multiple extra dimensions tied into each of these different subspaces that are associated with each dimension, shown by these sporadic groups, which is something that's truly mind-boggling. So you can effectively become invisible, if you will, by raising yourself up. Suppose you're in a two-dimensional space. If you raise yourself up into the third dimension looking down, no one can see you. You're invisible. But all you've done is you've gone to one of these adjacent dimensions that the other people don't realize is there. And so it goes. So having said that, we have this funny thing with these two dimensions, one for matter, where time, the matter for time, is in fact constantly branching. We're following a many worlds interpretation of time, is constantly branching. At each instant, there's a change of state, and there's many, many timelines, but by and large, they appear to coalesce about one or more paths that can be shaped by free will that can change over time. This is what Nostradamus saw, and other people, that there are potentially a variety of timelines. Nostradamus saw a timeline for our world that involved Hitler, and before Hitler was Napoleon, and after Hitler was the Antichrist. Now, by publicizing this, Nostradamus wanted us to change the time. And in fact, the Antichrist probably was born in the 1950s, 1960s. He's probably still alive, but he hasn't had nearly the impact that Nostradamus saw, that we were able to change that. Dark matter time is a different matter. This doesn't have the branching behavior we're talking about here of matter and time, but dark matter time is the Akashic record of a particular soul or spirit. It starts at the beginning. It's a thread that starts at the beginning of the universe and ends when the next bounce occurs. So it is invisible to the mind, the conscious mind of matter here. But when you go into deep hypnosis or deep meditation, you can link to your soul, and this provides access to this timeline. So you can see incarnations of your soul, you can regress back to an earlier life, and you can also see what happened when you were in between incarnations. So time is very different than space here in what's going on. So with that, we'll call it a day, and thank you for listening.